Hey everyone, welcome to the third video in this series on Fanuc Focas programming. I know it's been a long time and I'm sorry it's taken so long. Life has gotten in the way, but I'm hoping to put out some more videos pretty soon. So today we're going to be covering what I think is one of the most important and used functions in the Focas library. The function we'll be demonstrating will be the PMC read PMC range function that is used to read signals being sent to and from the Fanuc PMC. If you just got done watching the previous video, or you just remember from when you watched it, we did say that we were going to go over the axis positions. However, that's not going to be the case. Instead, we're going to be going over the PMC stuff this time, and we will do the axis stuff in a future video. In this video, we will be learning what the Fanuc PMC is and what a PMC address is, as well as how to extract the information contained in the PMC that might be of use to us. First, we need to define some terms. The first term we need to define is CNC. In this case, the CNC is going to refer to the Fanuc controller. This is the piece of hardware that controls all the functions of the machine. It's responsible for taking user input and making the machine move. Second is machine tool. The machine tool is going to be the router, robot, mill, lathe, or other physical piece of machinery that the CNC is controlling. Lastly is PMC. PMC stands for Programmable Machine Control and is an interface between the CNC and the machine tool. It contains ladder logic that is used to control the various functions of the machine and send signals back and forth between the various components. So, for instance, the machine tool may have a button that resets the program and puts the CNC back into idle. The button press will send a signal from the machine tool to the PMC. The PMC will then determine what to do with that signal via the ladder logic that is provided by the machine tool manufacturer. In this case, the PMC will forward the signal onto the CNC. It is these signals that we want to read. Each of the PMC signals is correlated with a PMC address. A PMC address consists of two parts. The first part is a letter that designates the address type, and the second part is a decimal that is used as an index. The letter or type portion of the address tells the user where the signal is coming from and going to. For instance, an F represents signals traveling from the CNC to the PMC. A G address is a signal traveling from the PMC to the CNC. We also have letters for physical inputs and outputs, which are represented by X and Y respectively. There are other address types, but these are the ones that we're going to be most concerned with. Others that you may need are K, R, and E, which stand for keep relays, relays, and extended relays. Let's look at an example to get an idea of how and why we would use any of this. Imagine you want to know whether or not your machine is currently running a program or MDI command. We could read the cycle counter to see if it's counting up, but this is rather hacky and cumbersome. It would be vastly easier if we had a signal that told us whether or not the machine was running. Luckily for us, there is. Looking through the address list in the manual provides us with a signal called the automatic operation signal. This signal turns on when the machine is running and turns off when the machine exits a running state. The address of the signal is F0.7. In this case, F represents a signal coming from the CNC and going to the PMC. In other words, the Fanuc controller is telling the ladder logic that the machine has started running. The second part of the address, 0.7, is the index at which this particular signal can be found. The indexes consist of a location and a bit. The indexes are 0-based, which means that they start at 0 instead of 1. In this case, our signal can be found on bit 7 of the first index. If we were looking for the reset and rewind signal, We could find that at G8.6. This would be a signal coming from the PMC and going to the CNC, which resides on bit 6 of the 8th index. Now that we have a basic understanding of the PMC and the PMC addresses, we can take a look at how to read these signals using the Focus library. We will be utilizing the read PMC range function to read these signals. I will be referencing the EventCom page throughout this video to demonstrate how to use the information provided there. The page is linked below in the description if you want to follow along. The function call has slight variations based on the type of control you have, so you may need to reference different sections than me. I will be looking at the materials related to the 31i controller type. If you have a different controller, you will want to find the correct table for your control type. Since we know what the function call is, we will skip the description on this page. You can take a look at the declaration to get an idea of what is needed for this function call. We will be moving straight to the argument section to go over each of the arguments one by one. As normal in a focus call, the first argument is going to be the focus handle we got when we first connected the controller. The next argument is going to be the address type. As we discussed earlier, this is going to be the letter that tells us where the signal is traveling from and to. However, we are not going to be providing the letter as a string or a character. Instead, the function call requires us to supply the letter as a short. In the address type section, which is quite long, is a series of tables which are separated by controller type. In this case, I'm going to skip down to the table for the 31i controller. If you have a different controller, find the table that is applicable for your controller type. Looking at the table, we can see an ID code, kind of PMC address, and some columns showing the index ranges. The only rows we care about right now are going to be the first two. Instead of supplying the function with the letter, we are going to use the ID code, which represents each of the PMC address types. If we wanted to read the reset and rewind signal, which is a G address, we would put a 0 as the second argument. If we wanted to read the automatic operation signal, which is an F address, we would use 1. The next argument is going to be the data type. The data type is going to be the size of the PMC data. In the manual, we will find a chart that shows us how big the section of information we want to read is. The automatic operation signal is represented in the manual by OP. We know that OP is at F0.7. We locate F000 in the chart and we can see OP at bit 7. Unfortunately, the smallest unit we can read from the controller is a byte. So even if all we need is a single bit, we first have to read the entire byte and then extract the bit we need afterwards. However, some signals take up more space, such as the manual feed rate override signal, which takes up 16 bits or 2 bytes. This is also referred to as a word. So if we wanted to read this signal, we would need to use word here. Again, this argument needs to be a short, so we'll use the number next to each data type for the function call. In this case, it's going to be 0. The next two arguments are the start and end indexes. If you are reading a single byte, then these two are going to be the same. In the case of the automatic operation signal, we would use 0 for both. For the manual feed rate override, which spans 2 bytes, G10 and G11, we would put 10 for the start and 11 for the end. For the length, we need to do some math. Don't worry, this isn't anything complicated. We just need to know the number of indexes we want to read and plug this into the given formula. For the automatic operation signal, we are reading a byte, so we will use the first formula. Length is equal to 8 plus the number of indexes we want to read. If we were reading the manual feed rate override signal, we would use the second formula for word. Length is equal to 8 plus the number of indexes we want to read multiplied by 2. The last argument for this function is going to be an instance of the IODB PMC structure. This is what is going to hold all the information about this PMC address. It contains all the basic information such as the kind of address, data type, as well as the start and end addresses. However, the part of the structure we are interested in is the union that contains the information. The structure, as shown on the page, is in C and shows the union containing C data, I data, L data, F data, and DF data. Since unions don't exist in .NET, there is some messiness that occurs between the C library and the C# implementation. The important thing to remember is that the data type of the address will determine which of these you need to read in order to get the information. So, if we obtain a single byte, such as when we read the automatic operation signal, we will use C data to get our information. If we read the manual feed rate override signal, we will use the I data field instead. Because unions don't exist in C#, we will use a different IODB PMC structure for our call depending on the data type we're reading. If you're trying to read a byte, we will need to use the C data field, which is contained in the IODB PMC 0 structure. I data is contained in the IODB PMC 1 structure, and L data is contained in the IODB PMC 2 structure. I realize this can be a bit confusing, but don't worry if it's not perfectly clear to you. We'll do a couple of examples to help it sink in. Alright everyone, let's get to an example. So you'll notice this is a code from the previous video. If you haven't watched the previous videos, please go back and watch them. It's really important that you have the understanding, the basic understanding of how to connect, and you have all the files in place to be able to connect to the controller. So we're going to be trying to read the automatic operation signal, which, if you remember, is F0.7. So the first thing we are going to do is create a new function. We're going to create a public static. It's going to return a bool, and we'll just call this getOpSignal. So the first thing we need to do whenever we are making a focus call is we need to check to see if the handle is equal to 0. If it is, we are going to write a line, and we're going to just say error, please obtain a handle before calling this method. Alright, and then we'll return false here. Now that we have that, we're going to create a couple of variables just for the sake of clarity. So we're going to create a short, and we're going to call this address kind, and we're going to set this to 1. If you remember, 1 is F. We are also going to create another short called data type, and this is going to be a byte, so that's 0. Then we're going to create a uShort. We're going to call this start, so this is going to be our start address, and remember it's F0.7, so our start address is going to be 0. We'll do another uShort, we'll call it end, and we'll also set that to 0. So because we are only looking at index 0, the start and end are going to both be the same. If we were trying to read another address that took up, say, 2 bytes, we would put the start and end, and they would be different. Next, we are going to do a uShort and call it data length, and we're going to set this to 9. Now, if you remember, our formula is going to be 8 plus n, n being the number of indexes we want to read. So that's going to be our data length. Last thing we need to do is we need to create a focus1.iodb PMC 0. It's going to be 0 because we're reading a byte. If we were reading a short, it would be 1, and if we were reading a integer, it would be 2. So in this case, we're going to do 0, and we'll call this PMC equals new. Alright, there we go. Now we get to our call. So, of course, we're going to do ret, which is going to be our return code, because we always need to check the return code. Focus1, PMC, read PMC range, right there. The first thing we always give to our function is going to be the handle. We're going to give it the address kind. We're going to give it the data type. We're going to give it the start address, the end address, and our data length. And then we'll give it our PMC, and we're good. Now, we are going to check our return code against focus1 EWOK, which is 0. So a 0 return code is good. And we're going to do console.writeLine, and we'll do error, unable to obtain the OP signal. Alright, and then we'll return. Now I have added some extensions. Basically, they're called getBit, and it's doing a little bit of bit shifting to read a specific bit out of this byte. If you need this, I'll upload it to GitHub, so you can all have it. So, in order to get this bit, what we're going to do is we're going to say return, and we're going to say PMC .cdata, and now this is an array. So we're always going to read the first element of the array. Get bit, and we want bit 7. Now that we have this, I've added in here a thread that calls a function called exit check that will run in a loop, and it will check to see if we type exit into the console. Now, the reason I have that is because I want to be able to set this, I want to be able to exit this while loop at the end. So, what we'll do is we'll do console.write, and I'll do, so we're just doing this so it overwrites the line continuously instead of doing a new line. Signal to string. We'll also do a that way we're only checking it every 500 milliseconds or so. So this looks good. Let's go ahead and start it and see what we get. Alright, so as you can see, it's reading the op signal as false. If I come over to my FANUC, notice the X distance in the top right. If I hit cycle start, it starts counting down, and you can see that op signal is now true with an extra E. It just flipped back to false. So that is how we read the op signal. Now that you've seen an example of how this function call works, I have a little bit of homework for you. I want you to go through your maintenance manual and look at all the F and G signals. There's a whole list of them in there. In my case, it's from pages 357 to 370. Your manual may be different. It's not going to list X and Y addresses. I think there are a few X addresses that are static, but for the most part, they are going to be machine independent. So whoever wrote your ladder logic controls the X and Y signals. You may be able to get a list of X and Y signals. X are going to be mostly button presses and sensor readings, and the Y's are going to be outputs that fire solenoids and stuff like that. If you have any questions, let me know. I'll gladly try to help out. Thank you guys for watching. Like, comment, subscribe. I really hope these videos have been helpful to people. If they have, please let me know. Till next time.